Imagine two tiny particles, one here on Earth, the other drifting near the distant Andromeda galaxy, separated by millions of light-years. Despite this unimaginable distance, these particles share a mysterious connection, as if they're engaged in a silent cosmic conversation that transcends space itself. If you nudge the one here, just the slightest touch, something extraordinary happens. Could its distant twin, light-years away, instantly feel it, reacting in perfect harmony, as if no space separates them at all? This isn't science fiction, it's one of the most profound and mind-bending mysteries in all of physics, challenging what we think we know about the universe. It shakes the very foundations of our understanding of space, time, and reality itself, forcing us to rethink what's possible. According to quantum mechanics, particles can become entangled, linked in such a way that their states are intertwined, no matter how far apart they are. This connection seems to defy the rules that govern the rest of the universe. This strange link appears to break the universe's ultimate speed limit, set by Einstein's theory of relativity, which says nothing can travel faster than light. Yet, countless experiments show that entangled particles act as if distance simply doesn't matter. Their connection is instant, mysterious, and unbreakable. What if, at the deepest level, everything in the universe is woven together in a vast, invisible cosmic web, where every part is linked to every other? This isn't just a philosophical idea, it's a scientific revolution, changing the way we build technology and how we see our place in the cosmos. We're about to explore quantum entanglement, a discovery so strange, it redefines what we mean by reality itself. Get ready to question your deepest assumptions about how the universe works. The story of entanglement is about the very fabric of reality, how everything might be connected in ways we're only beginning to imagine. Are you ready to enter a world where two particles can dance in perfect sync, no matter how far apart they are? The journey into quantum entanglement begins now. Albert Einstein famously called this phenomenon spooky action at a distance. The phrase captures both his fascination and his deep discomfort with what quantum mechanics seem to suggest about the universe. According to quantum theory, two particles once entangled remain mysteriously linked no matter how far apart they travel, even if they end up on opposite sides of the galaxy. If you measure the state of one particle, you instantly know the state of the other, even if it's 1,000,000 miles away, or more. It's as if information leaps across space in an instant, defying all logic. There's no signal, no time delay, and no obvious way for the particles to communicate. The effect is truly instantaneous, as if space itself doesn't matter. To Einstein, this was absurd, like magic, or a trick of the universe that defied everything he believed about how reality should work. It violated his cherished principle of locality. The idea that nothing should be able to influence something else instantly across space. For Einstein, this principle was a cornerstone of physics. He believed the universe should be rational, with clear causes and effects where information and influence travel no faster than the speed of light. But spooky action seemed to throw all that out the window, shattering the neat, orderly picture of reality that Einstein cherished. For decades, many physicists chose to ignore this bizarre prediction, treating it as a strange quirk of the math, something that didn't need to be taken too seriously. But Einstein couldn't let it go. He was convinced that quantum mechanics, as powerful as it was, must be incomplete, missing some deeper explanation. He argued that particles must carry hidden instructions from the start, secret information that determined their behavior even before they were measured. The mystery of spooky action set the stage for one of science's greatest debates, pitting Einstein against the strange predictions of quantum theory. Was the universe truly non-local, with connections that defy space and time? Or was something fundamental missing from our understanding of reality? This question would haunt physics for decades, challenging scientists to rethink the very nature of space, time, and information. The answer, when it finally came, would change our view of reality forever, opening doors to new technologies and new mysteries. The debate was just beginning, and the world of physics would never be the same. The debate over quantum mechanics was a clash between two giants, Einstein and Niels Bohr. Einstein believed in an objective reality. Things exist whether we observe them or not. Bohr argued that a particle's properties don't exist until measured. Reality is created in the act of observation. Entanglement was their battleground. Einstein saw it as proof that quantum mechanics was incomplete. Particles must have preset properties. Bohr embraced the strangeness. Entangled particles are not separate but part of a single quantum system. Measuring one instantly affects the whole system because it's all one. Their debates were legendary. Einstein's thought experiments versus Bohr's quantum logic. Each challenged the other's deepest beliefs about reality. The question, is the universe fundamentally predictable, or is it shaped by the act of observation? This struggle defined the soul of modern physics. The answer would come not from philosophy, but from experiment. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, introduced what would become known as the EPR paradox, a bold challenge to the very heart of quantum theory. They questioned whether quantum mechanics could truly describe reality, or if something deeper was missing from the picture. To illustrate their point, imagine a pair of gloves, one left, one right. You place each glove in a separate box, then you send one box to a friend at the farthest corner of the world, say, Antarctica, while you keep the other with you. When you open your box and discover a right-handed glove, you instantly know, without any doubt, that your friend's box must contain the left-handed glove, even if they're thousands of miles away. There's no magic at play here, and certainly no mysterious signal traveling faster than light. The handedness of each glove was determined from the very beginning, before the boxes were ever separated. Einstein argued that entangled particles in quantum mechanics are just like these gloves. Their properties are set in advance, simply hidden from us until we look. According to him, the apparent randomness and unpredictability of quantum mechanics is not fundamental. Instead, it's a reflection of our ignorance. There are hidden variables, unknown factors that determine the outcome. The EPR paper concluded that quantum mechanics, as it stood, was incomplete. Unless it could account for these hidden elements of reality, it could not be considered a full description of nature. This sparked a fierce debate among physicists. They faced a profound choice: either accept the strange, spooky action at a distance predicted by quantum theory, or believe that the theory was missing something essential. For Einstein, the answer was clear and unwavering. Reality must be both local and real, not subject to instantaneous influences from afar. The paradox forced Niels Bohr and his followers to defend the very foundations of quantum theory, leading to passionate arguments and new experiments. The stage was set for a revolution in physics, a journey that would challenge our understanding of reality itself. Einstein's resistance to entanglement was rooted in his belief in local realism. Locality, nothing can influence something else instantly across space. Realism, things have definite properties, whether or not we observe them. Quantum mechanics, with its randomness and instant connections, violated both. God does not play dice with the universe, Einstein famously declared. He believed hidden variables would one day explain the apparent weirdness. Entanglement, to him, was the ultimate offense, defying both locality and realism. He saw it as a temporary puzzle, not a fundamental truth. The EPR paradox was his challenge to the physics community. Quantum theory works, but what does it really mean? Einstein never accepted a universe where reality was fuzzy and connections were instantaneous. But the universe had more surprises in store. For decades, the Einstein-Bohr debate was philosophical, impossible to test. Then in 1964, John Bell changed everything. Bell showed that if hidden variables existed, there was a strict mathematical limit, Bell's inequality, on how strongly entangled particles could correlate. If quantum mechanics was right, those correlations would break the limit. Bell's insight turned a philosophical argument into a testable experiment. Measure entangled particles in different ways, and see if the universe obeys Bell's inequality. If it does, Einstein was right. If not, Bohr's quantum weirdness wins. For the first time, physics could ask the universe, are you local and real, or truly spooky? All that was needed was an experiment precise enough to decide. The stage was set for a showdown with reality itself. After Bell's breakthrough, physicists raced to test his inequality. Early experiments in the 1970s hinted at quantum mechanics being right, but had loopholes. In 1982, Alain Aspect's team closed those loopholes with a brilliant experiment. They created entangled photons, measured them with fast, random settings, and ensured no signal could pass between detectors. The results were clear. Bell's inequality was violated every time. No hidden variables, no local realism, just quantum entanglement. Countless experiments since have confirmed it. The universe is indeed spooky. Einstein's intuition was defeated by nature itself. Non-local connections are not a bug, they're a feature of reality. Quantum mechanics had passed its ultimate test. To understand entanglement, meet two quantum ideas, spin and superposition. Spin is like a tiny top, up or down, but in quantum mechanics, it's not fixed until measured. Superposition means a particle exists in all possible states at once, like a coin spinning in the air, both heads and tails. Now entangled two electrons, their total spin must be zero. Before measurement, neither has a definite spin. Both are in superposition, but they're linked. Measure one is up, the other must be down, instantly, no matter the distance. It's not a signal traveling, it's that they were never truly separate. They're two sides of one quantum coin. Measuring one instantly reveals the other, because they share a single quantum state. This is the non-local dance of entanglement. Reality, at its core, is more connected than we ever imagined. The rules of the quantum world defy our everyday logic. Yet, they are the rules the universe follows. Entanglement isn't just a curiosity, it's powering a technological revolution. Quantum computers use qubits, which can be 0, 1, or both at once, thanks to superposition. Entangled qubits can solve problems that would take classical computers billions of years. This could transform medicine, materials, and AI. Quantum cryptography uses entanglement for perfectly secure communication. Any eavesdropper is instantly detected. Even quantum teleportation is real. The state of one particle is transferred to another, far away, using entanglement. We're at the dawn of a quantum age. The spooky action that troubled Einstein is now a tool for the future, but a deeper mystery remains. Why is the universe built this way? What other hidden connections are waiting to be discovered? As we unlock these secrets, we're only beginning to understand the true fabric of reality. The quantum revolution has just begun. The universe is stranger, and more wondrous, than we ever imagined.